Hello. In this video, we are going to introduce the topic of improper integrals. So, to introduce this topic of improper integrals, we're going to look back at where we started with integrals back when you first learned how to evaluate integrals in Calc 1 and recall the fundamental theorem of calculus. Fundamental theorem of calculus says if f is a real valued continuous function on a closed interval a to b, and capital F is an antiderivative of f in that closed interval a to b, then the integral from a to b of f of t dt is equal to the antiderivative with a and b plugged in. F of b minus f of a, upper bound minus lower bound. And we've been using this repeatedly. Improper integrals ask the question, what if a couple of things of these are changed? What if the interval isn't continuous? Specifically, there is an asymptote. And what if our interval isn't closed, but is instead an infinite interval? Say we have from some value a until infinity. Can we still evaluate these integrals if the interval isn't continuous, or the function isn't continuous on the interval? And what if that interval is infinite? The first question, what if the function isn't continuous, will be addressed in type 2 integrals. So we're going to look at those second. But what if the interval isn't finite, or we have an infinite interval? This is what is known as a type 1 improper integral. So, as a first example, suppose we want to look at the area under the curve of 1 over x cubed on the interval 1 to t where t is bigger than 1. The area under the curve is the integral. And we're saying t is just some real number. So we're looking at the integral from 1 to t of 1 over x cubed dx, which is 1 to t of x to the negative 3 dx. Evaluating that integral, it is negative 1/2 x to the negative 2 from 1 to t, plugging in the bounds by our fundamental theorem of calculus. We have t to the negative 2 minus negative 1/2, 1 to the negative 2. And some algebra simplifications, this becomes negative 1 over 2t squared plus 1/2. Well, the first question we're trying to ask is, what if I didn't have a finite interval? What if my interval was, say, 1 to infinity? Well, this idea is telling me that I could put in larger and larger values of t, and I would get closer and closer to the interval 1 to infinity. If t equals 2, then the integral from 1 to 2 of 1 over x cubed dx is -1/2 times 2 squared plus 1/2. If t equals 10, we get the integral from 1 to 2 of 1 over, 1 to 10, 1 over x cubed dx, which would equal -1/2 10 squared plus 1/2. And if we evaluated this out, as we keep increasing these t's, this first fraction keeps getting smaller and smaller. Right, this first fraction here, -1/2 times 2 squared would be -1/8. -1/2 times 10 squared would be -1/200. 1, 2, 3, 4 zeros plus 1/2. This first fraction in each of these keeps getting smaller. So as t goes to infinity, the integral becomes closer and closer to 1/2. This means for us that if I wanted to know the integral from 1 to infinity, I can't plug infinity into a function, but I can look at the limit as a variable goes to infinity. And that, I was able to find this part to be the equation -1/2t squared plus 1/2. And the limit as t goes to infinity of that is right here. And that equals 1/2. Meaning the area under the curve of 1 over x cubed from 1 to infinity is 1/2. This gives us a strategy for evaluating integrals where I have an infinity in a bound. So improper integrals of type 1 would be these functions. They're continuous from a to infinity, but we're going to infinity, or we might have a negative infinity. In these cases, how we handle these integrals is we look at the limit of that infinity bound. We can evaluate these integrals just as normal and then take the limit, and either we'll get a undefined limit or a limit of infinity, or we'll get a number. Or if our lower bound is negative infinity, we'll switch out the negative infinity to be a limit. And if we have from negative infinity to infinity, we're looking over the entire number line, we will split up the integral into 2 pieces, picking a random number in the middle, probably regularly 0, if it's easy to work with, and just split up our integral into 2 pieces, and now we have a lower bound of infinity that we can evaluate. And we have an upper bound of infinity. Where we can use the improper integral strategies. So let's take a look at another example. We want to find the area under the curve of y equals 1 over x for x greater than or equal to 1. This is saying our interval is 1 to infinity. So we are trying to find the integral 1 to infinity of 1 over x dx. First thing, for an improper integral, we have to turn it into a limit. To use the fundamental theorem of calculus, we need the bounds to be real, technically finite numbers. So we're going to switch out that infinity for a limit, and now we can just evaluate. The integral of 1 over x is the natural log. So we still need the limit. T goes to infinity of the natural log of x, absolute value of x, from 1 to t. Plugging in the bounds, and then as t goes to infinity, the natural log of the absolute value of t minus the natural log of the absolute value of 1. The natural log of the absolute value of 1 is 0. However, the limit as t goes to infinity of the natural log of t is infinity. This is infinity. So this limit goes to infinity. Saying that the area under that curve is infinite is something we can say, but we actually introduce new vocabulary here, where instead of saying the area is infinite or the integral equals infinity, we're going to use some words that are converges or diverges. So introducing this vocabulary here. If the integral with our bounds, I'm going to leave them as a and b, because the type 2 integral might have a type 2 integral does not have an infinity bound, but we use this vocabulary for type 2. So if we have an integral and it comes out to some number L, where L is finite, then we say the integral converges. Integral. If the integral does not converge, meaning we get a limit that is infinity or the limit does not exist. So if integral does not converge, we say the integral diverges. So using that vocabulary on this problem actually gives us the integral from 1 to infinity of 1 over x dx using this language. It does not come out to a finite number, so it does not converge, meaning this integral diverges. Going back to apply this wording to the previous problem we looked at. Applying this wording on this problem, we did get a number at the end. So the integral of 1 to infinity of 1 over x cubed dx converges. We get a number at the end of our limit, and it converges to 1/2. There is our new wording. There is actually a rule for these types of integrals we're looking at, and these are any integral of the form some lower bound to infinity, 1 over x to the p, where p is a number. These integrals will converge if p is bigger than 1, and it's going to be strictly bigger than 1. So the integral from 1 to infinity of 1 over x squared dx converges. The integral 1 to infinity of 1 over x to the 1.1 converges. The integral from 1 to infinity of 1 over x to the 100 converges. So we know that for all p greater than 1. And then it diverges if p is less than or equal to 1. So we see here the integral from 1 to infinity, 1 over x dx diverges. We also would know the integral. We can start it even at 2 to infinity of 1 over the square root of x dx will diverge. So we know this fact. This fact is called the p-series test for integrals. Making this something we can use for these very specific forms of integrals. And we will see in a later video how we can apply this to other integrals.